special triangle. So from the unit circle and special triangles, we could develop values for sine at certain degrees, okay, or cosine at certain values, and tan at certain values. You don't have to memorize this table. All you have to do is be able to draw the special triangle. So we're just going to review what the special triangles are. So we have a 45-degree triangle. The radius will be 1, the y value will be root 2 over 2, x value root 2 over 2. Okay, and if we're talking about radians, then instead of 45 degrees, we write it as pi over 4. Okay, other special triangle, 30-degree triangle. Radius is 1, x value would be root 3 over 2, y value would be 1 over 2. In radians, we had pi over 6. Okay, and the third special triangle was 60 degrees. Okay, radius is 1, our x value will be 1 over 2, our y value will be root 3 over 2. And in radians, we have pi over 3. So these three triangles will come in handy throughout this entire lesson, so I figure we just have it on the side and you guys will be able to look at it the whole time. Rather than having to memorize that sine 45 is root 2 over 2, we can just look at our triangle and go sine 45 degrees, that's the y coordinate, root 2 over 2. Okay? So to figure out if something is an identity or not, the left-hand side has to equal the right-hand side, and there's just a few examples showing if it is the identity or not. Rather than wasting some time proving that this actually didn't work, I might just jump to showing which ones do work. So just to explain a little bit what's happening here, they chose values 60 degrees and 30 degrees and replaced A and B with 60 and 30 and proved that this side did not equal that side. Okay, so this is not an identity. Sine A plus B is not sine A plus sine B. Whereas if we go into these examples, we are proving what the identities are. So let's just go right to the ones that work. Okay, so sine 60 plus 30 degrees. If we look at the left-hand side first, we have 60 plus 30 is 90 degrees. Okay, the value of sine 90, we had 90 degrees here. We're rotating all the way up. The x-coordinate would be 0, the y-coordinate would be 1. Sine, is that an x-coordinate or a y-coordinate? You guys remember? It's the y-coordinate, opposite. Okay, so that's going to be equal to 1. Or you could just put sine 90 in your calculator, you'll get 1. So left-hand side is 1. Let's see if we also get 1 on the right-hand side. So looking at the exact values, let's go to our special triangle. Sine 60, that's going to be the y-coordinate, root 3 over 2. Okay, cosine 30. Look at the special triangle for 30 degrees, and cosine is always the x-coordinate, adjacent over hypotenuse. So we have root 3 over 2. Okay, Emily, help me out with cos 60. What's the value? Don't look at the table. Look at your special triangles.
X.
So it should be an exact value. So looking at the special triangle 60, is cosine going to be this, this, or this?
1 over 2.
Yeah, good. And just to help you out, cosine is always adjacent over hypotenuse, right? So here's my adjacent divided by my hypotenuse. The 1 doesn't matter. We just have 1 over 2. Okay? Okay, now let's look at sine 30. Emily, I'm going to see if you got it. We're now on the special triangle, 30 degrees. What would sine 30 be?
1 over 2.
Perfect, 1 over 2. It's the y-coordinate. Okay, so root 3 times root 3 is 3. Denominator, 2 times 2 is 4. Okay, in the second term, we have a half times a half. That gives us 1/4. So 3/4 plus 1/4, that equals 1 whole. So 1 equals 1. Left-hand side equals right-hand side. So we've just proven that this could be, or this is the identity, the sum identity for sine. And I'll just go through that with you guys here. Okay, so sine A plus B is equal to sine A cosine B plus cosine A sine B. This is not something you have to memorize, but the more you practice it, the easier questions are going to come. Okay, this is on your formula sheet. You don't have to memorize it, but try and memorize it if you can. Okay, so just keep in mind when you have the sum identity for sine, you have an addition in between. Okay, let's look at the second example now. Okay, so we have sine 60 minus 30 degrees. If you guys prefer, do you want to just put these in degrees? Or is it okay we leave them in radians? We know that's 60 and that's 30? Okay, then we can roll with it. Okay, so we have 60 minus 30. That leaves us with sine 30. We're just looking at the left-hand side right now. Sine 30 degrees. Xander, can you help me? What's sine 30? What's the ratio for sine? Is it opposite over hypotenuse, adjacent over hypotenuse? So opposite over hypotenuse, we just have 1/2, okay? So now let's see if the right-hand side is equal to that. So we have sine 60 degrees. Okay, go to our special triangle for 60 degrees. Sine is the y-coordinate, √3/2. Okay, cosine 30 degrees. Let's take a look at our special triangle. Cosine is the x-coordinate, we have √3/2. Okay, cosine 60 degrees. Down at the bottom, it's the x-coordinate 1/2. And we're multiplying by sine 30 degrees, which is also 1/2. So we have √3 times √3 is 3/4. Subtract 1/4. That gives us 2/4, which is 1/2. So 1/2 equals 1/2. Left-hand side equals right-hand side, so we've proven the identity. So this is the difference identity for sine. Sine A minus B is equal to sine A cos B, subtract cosine A sine B. Okay, so just to help you guys out a little bit, with sine it's always going to be AB, and it goes sine, cos, cosine. It's on your front of the sheet though, so don't worry too much about it. How are you guys finding using your special triangles to prove sum and difference identities? Do you think we need to use exact values to prove that these are the cosine sum and difference identities?
The triangles work.
Pardon?
Triangles work, I think.
So you're happy with triangles? We don't need to do any more examples? Or do you want to go through a few more?
I think they're fine, yeah, I'm good.
Okay, does anyone else want to go through how to prove the cosine sum and difference identities? Then we're going to roll on. Okay, so in summary, we have the sum identity for sine, which is here. Okay, sum means add. We have the difference identity for sine, so it means subtract. And we also have the sum identity for cosine and the difference identity for cosine. Now one thing that you need to note with sine, if it says addition, you're adding. Okay, subtraction, you're subtracting. But with cosine, it's a little bit different. For the sum identity, if we have A plus B in the statement, it's going to be subtraction. And if we have A minus B, it's the opposite, we have addition. Okay, so just be aware if you make a mistake with the plus and minuses, it's going to throw everything off. So be very careful when you're looking at your formula sheet and make sure you get the plus and minuses correct. Okay, so there's 4 sum and difference identities for sine and cosine. The next little bit is showing us how to derive the tan sum and difference identities. I'm not going to do both examples because this one's pretty repetitive, but I'll show you how to derive the first one for the sum identity for tan. Okay, so for tan A plus B, we have to remember the quotient identity. I don't know if you guys do remember or not, but the quotient identity for tan is equal to sine theta over cosine theta. So we're using that identity and we're taking tan A plus B and we're applying the quotient identity and turning it into sine A plus B over cosine A plus B. Up top, sine A plus B, that is the sum identity for sine. And the sum identity for sine is given as sine A cos B plus cos A sine B. In the denominator, we have the sum identity for cosine. And that is equal to what we have in the denominator here. Okay, the next step is we're going to divide the numerator and denominator by cosine A and cosine B. So that's just what they've shown here. So if you apply something to both the numerator and denominator, then you're allowed to do whatever you want. Okay, because this is equivalent to 1. We haven't changed the value of this at all. So getting a little bit creative to manipulate a bit further, and eventually we're going to be proving the tan identity. Okay, so let's just roll forward. We're going to apply this denominator to both terms in the numerator. Sine A cosine B over cosine A cosine B plus cosine A sine B over that same denominator, cosine A cosine B. Okay, that's just the numerator. Now we have to apply cosine A, cosine B to both terms in the denominator.
And so, like, what's our end goal right now?
Our end goal is we're trying to prove this identity at the very bottom. And I'm just showing you this example because you have to show a little bit of creativity to come up with this step. And it's just one way of manipulating a statement to get the end result that you want. Okay, so you won't have to do this every time because the identities will be given to you. But it's just one way of showing how you can manipulate a statement. Okay. Alright, so in the denominator we have cosine A cosine B divided by cosine A cosine B. And last but not least, we're subtracting sine A sine B divided by cosine A cosine B. So why we've done this step is because the end result, which you can see at the bottom of the page, we need tans. So in order to achieve tans, we have to have sine over cosine. And before we can do that, we had to apply cosine in the denominator. And now that we have, let's just see if we can cancel anything out. So in this first term, cosine B cancels out. In the second term, cosine A cancels out. Looking at the denominator now, in the first term, cosine A cancels out, cosine B cancels out. And in the last section there, nothing cancels out. So we're left with sine A over cosine A plus sine B over cosine B. All over 1 minus, okay, if these all cancel out, it becomes 1. And we're subtracting now sine A over cosine A times sine B over cosine B. You could just write it like this too. Booker, any questions?
No, I just didn't know where you were getting the first stuff, but you just broke it up. I understand
Here?
now. Yeah.
So yeah, we just applied this denominator to
Yeah.
the first term and this denominator to the second term.
I was just trying to figure out where you got it, but yeah.
Sorry, I maybe said that too quick. Okay, last step. We're going to use the quotient identity and we're going to take all the sine over cosines and make them tans. So here we have a sine over cosine. That can be tan A now. Okay, Okay, here we have a sine over cosine, so we have tan b. And in the denominator, we have 1 minus. Here we have sine over cosine, same variable, so sine A over cosine A is tan A. Multiplied by sine B over cosine B is tan B. And that is the sum identity for tan. Now, it's very unlikely that you guys will have to derive this identity. It's going to be given to you on your formula sheet. But I just wanted to show you this one step, just in case you do have to manipulate something. Okay, it's just showing that you can apply the same thing to the numerator as the denominator and not change the value. So in conclusion, we have the tan sum identity, which is on the left here, and we didn't derive it, but it's given here, the difference identity for tan. The only difference is, for subtraction, we have subtraction on top and addition on the bottom, and for adding, we have addition on the top, subtraction on the bottom. Okay? Everything else is the same. So you have to be careful with your plus and minus lines. Alright, so some questions that you're going to see with the sum and difference identities would be like these. So express 15 degrees as a difference of two special angles, and hence determine the exact value of sine 15 degrees with a rational denominator. Okay, so as a difference of two special angles, first of all, if you think of difference, you want to kind of clue in, oh, I'm going to need my difference identities. Okay, and then special angles, that's kind of a hint to think about special triangles. Okay, and then lastly, we just need to figure out what the value of sine 15 is. So can we put any combination of 45, 30, and 60 where we're taking a difference so that we result in 15 degrees?
45 minus 30.
Okay, good. 45 minus 30, or we could have gone 60 minus 45. Okay, either or. But we'll just go with the 45 and 30. So sine 45 degrees minus 30 degrees is a difference identity. And maybe I'll just write it underneath. So sine A minus B is equal to sine A cosine B minus cosine A sine B. Okay, what is our A in this example? 45, and our B is 30 degrees. So we're just replacing the A's with 45s and the B's with 30s. Okay, so sine 45 minus 30 equals sine 45 degrees cosine 30 degrees minus cosine 45 degrees times sine 30 degrees. And again, we can use the special triangles to get the exact values and then hence find the result of sine 15. Okay, 45 minus 30 is 15 degrees. And now let's just look at our special triangles. So sine 45, root 2 over 2. Okay, you're looking at the y-coordinate of 45 degrees. Okay, root 2 over 2. Okay, multiplied by cosine 30. Cosine 30 is the x-coordinate on the special triangle, root 3 over 2. Okay, and then we'll subtract cos 45 degrees. Will be root 2 over 2 as well. And sine 30 degrees is 1/2. So when we multiply that through, root 2 times root 3 is root 6. 2 times 2 is 4. We have root 6 over 4. We're going to subtract root 2 times 1 is root 2. 2 times 2 is 4. Okay, and if we just clean it up, we can write it as root 6 minus root 2 all over 4. Okay, that's the value of sine 15 degrees. Just fine.
Brutal.
Alright, this next example, we have to express 5 pi over 12 as the sum of two special angles, and then hence show that cotangent 5 pi over 12 is equal to the square root of 3 minus 1 and the square root of 3 plus 1. Now, with the other class, what I did is I right away took cotangent and I used the quotient identity, and I changed that to cosine 5 pi over 12 over sine 5 pi over 12. And I resulted in like square root 2 or 6 minus 2 over square root of 6 minus square root of 2. Now, it actually equals the exact same value as this, but it's not what they wanted us to show. So if you go right into this, you're not going to get the correct result. It doesn't mean it's not the correct value, it is, but for this specific question, we're not going to use the quotient identity. We're going to use the tan value and then take the reciprocal to get cotangent at the end. Okay? So I'm just letting you guys know that because you might lead in one direction and it'd still be the same value, but it didn't get the actual numerator and denominator that was stated there. So just be careful. Sometimes you can lead in one direction that gives the same value, but it's not the correct way. Okay. I wasted the other class's time showing that mistake, and I won't waste your time showing you that mistake. So we're going to take this, and for me, I like working in degrees. So 5 pi over 12, that's actually 75 degrees. Our end goal is that we need to figure out what is the value of cotangent 75 degrees and prove that it equals root 3 minus 1 over root 3 plus 1. Okay, we need to show that it equals this. That's our end result. Okay, but we're not going to start with cotangent, we're going to start with tan. So tan 75 degrees. We need to write this as a sum of two special angles. So what two special angles can we add together to get 75? Good, 30 and 45. So tan 30 degrees plus 45 degrees, that gives us our 75. Okay, well this is an identity. It's a sum identity for tan. And I'll just write out that identity on the side here. So tan A plus B is equal to tan A plus tan B over 1 minus tan A tan B. Okay, this is the identity we're going to apply. So I'm just going to double check that I wrote it out correct. Yep. Okay, so our A is 30 degrees and our B is 45 degrees. So we're just going to replace the A's with 30 degrees, B's with 45. We have tan 30 plus tan 45. All over 1 minus tan 30 degrees times tan 45 degrees. Then we're going to look at our special triangles and get the values. So tan 30 degrees, opposite over adjacent. So if I have tan 30, that's going to be 1/2 divided by root 3 over 2. What happens to those 2's? Cancel out. So we end up with 1 over root 3. Okay, so tan 30 degrees is 1 over root 3. Now I've heard a little mumbling and groaning about rationalizing the denominator. In this case, if you do it, it's going to become a little bit too complicated. So I'm just going to leave it as 1 over root 3, okay, for simplicity. Because you'll go another 10, that's not going to result in this. Okay, so tan 30, 1 over root 3. We're going to add that with tan 45. Tan 45 is opposite over adjacent. So we have root 2 over 2 divided by root 2 over 2 equals 1. In the denominator, 1 minus tan 30. Have we already figured out what tan 30 is? Yeah. 1 over root 3. and multiplied by tan 45, which is just 1. Alright, so cleaning things up a bit, we have 1 over root 3 plus 1 over 1 minus 1 over root 3. So in order to get our end goal of root 3 minus 1 over root 3 plus 1, all we have to do is get a common denominator for both terms. So multiply by root 3 over root 3. And here we're going to multiply by root 3 over root 3. So in our numerator, we have 1 plus root 3 all over root 3. And in our denominator, we have root 3 minus 1 all over root 3. What's going to happen to those root 3's?
Smile here.
See you later. And we result with 1 plus root 3 over root 3 minus 1. We're really close, but we're not identical, and the reason for that is we've just figured out what tan 75 degree is. Okay, we haven't figured out what cotangent 75 degree is. Yeah, so we just flip it. Okay, so cotangent 75 degrees is the reciprocal of this. Root 3 minus 1 over 1 plus root 3. Therefore, we've proven left-hand side equals right-hand side.
What's that?
So the creativity in this one is you have to just think, well, how can I get rid of the square root of 3's in the denominators? And I just got a common denominator for those two terms.
You might also want to engineer.
Alright, so far in the lesson, we have seen the left-hand side of the identity, and then we've had to apply the right-hand side of the identity. Now what we're seeing is we're given the left or the right-hand side of the identity, and we need to simplify it to the left-hand side. So for example, what they're showing in part A is the right-hand side of the identity. We have to simplify that to the left-hand side. So I'll just write out the difference identity for sine. We have sine A minus B is equal to sine A cosine B minus cosine A sine B. Does this right-hand side look familiar? What is A and B though? 100 and B is 10. Okay, so if I were to replace this side with 110, which is already here, it would equal the right hand or left hand side. So we'd get sine 100 degrees minus 10 degrees. Okay, so this right hand side equals sine A minus B. So here, this equals sine 100 minus 10. I've just written it on a different side of the equation. Okay, it's not simplified yet though. We can subtract 100 minus 10. We get sine 90 degrees. And if we think of 90 degrees, that will put us to the point 0, 1. And the y-coordinate of sine 90 is 1. And you can just calculate that too. Sine 90 equals 1. Okay, so we've simplified. Now I'm just going to write over these values and see if you can figure out which identity you're using. Okay, which identity is it? Is it the sum, the difference of sine or cosine? So take a look at the identities over here.
Cosine.
Okay, good. It's cosine. Is it going to be the sum or the difference identity?
Difference.
It's the sum.
Is that not? That's. Oh yeah.
Because right here we have a subtraction sign.
I didn't know which one was.
Okay. So sum is adding, and difference is subtracting.
Yeah. I was, yeah.
But if you have subtraction, like if you have a subtraction sign, wouldn't it be for subtraction?
For the cosine one, it's a little bit opposite.
Oh, because there's, okay.
Yeah. So for this, the sum, you're actually subtracting. Okay? So just be careful with that. Alright, so if I had to simplify, forget about what's in the brackets right now. We just said that this is the sum identity for cosine. So that means it's going to equal cosine A plus B. Well, the A, if I erase this, was quarter of pi minus theta. Okay, and the B was a quarter of pi plus theta. So we just have to subtract and add to simplify. So we have a quarter plus a quarter, that's a half of pi, and the thetas cancel out. What's cosine 90 degrees? 0. And we simplify. Okay, so sometimes you can make these really easy. If you were to look at this at the beginning, who was a bit intimidated by all this stuff in the brackets? So sometimes it helps if you just simplify by making it all variables. Okay, and then you can see the identity a little bit easier. Okay, here we're given a few hints, and our end result is we need to figure out the exact value of cosine A plus cosine B. Okay, well first let's figure out the identity. So cosine A plus B is equal to cosine A, cosine B minus sine A sine B. Okay. Eventually you'll be able to just write that out, but for now you'll probably just refer to your formula sheet. So if we need the exact values, let's just take a look at what we already know. Well, they're giving us cosine A as 3 over 5. They're giving us cosine B as 5/13. So we know cosine A, we know cosine B. Do we know sine A and sine B? No. So we're going to have to draw a few pictures given the hints that they've provided. Okay, so for cosine A, they're telling us that A has to be between 0 and 90 degrees. So what quadrant are we in? 1. So we're going to draw a triangle. This is angle A, and they're telling us that cosine A, which is opposite over hypotenuse, is 3 over 5. So, did I say opposite? I meant to say adjacent. Okay, adjacent over hypotenuse. And then we're going to use the second hint about cosine B and look at the domain that they provide. So we're between 3 pi over 2 and 2 pi. So what quadrant? 4. Okay, it's between 270 and 360 degrees. So this will be for angle B. Okay, cosine B is 5 over 13. Adjacent is 5, hypotenuse is 13. So let's just fill in what we know. Cosine A plus B is equal to cosine A, cosine B minus sine A, sine B. Cosine A is 3 over 5. Cosine B is 5 over 13. And now we need to subtract sine A times sine B. Well, sine is opposite over hypotenuse. If we look at the triangle for A, do we have our opposite? Not yet. What will I use to find that third side? What is it? Pythagoras. Good. Okay, so we have x squared plus y squared equals r squared. In this case, we have to go r squared minus x squared to get our y squared. So, 5 squared minus 3 squared equals y squared. When we solve that, we get y equals 4. Okay, so this third side, y is equal to 4. So let's fill in what we know about sine A. Opposite over hypotenuse, the exact value will be 4 over 5. Now let's find the y coordinate for triangle B. Okay, hypotenuse is 13 squared. We're going to subtract x squared, so 5 squared, and that will give us y squared. When you solve for y, what do you guys get? 144? So y equals 12. Okay. So sine B will be opposite, 12, over our hypotenuse, 13. Now we just have to calculate and we'll get our exact value. Okay, so we have 15 over 65 minus 48. Oh, sorry, I need to correct myself. We're in quadrant 4. What will the y coordinate be, positive or negative? Negative. Okay, don't make that mistake, because you'll get your answer wrong. Alright, so we're having negative and then minus 48, also over 65. So this is actually like adding. So we have 15 plus 48, and that gives me 63 over 65. Okay, so the exact value of cosine A plus B is equal to 63 over 65. Rolling forward.